Hello everybody, my name is Dr. Fonseca and I will be presenting the paper OCR Post-Processing using Support Vector Machines. So let's get started on that. Okay, so first I'm going to talk to you about the OCR process, and then I'm going to give you a quick overview about possible ways of correcting OCR generated errors. And one of those is going to be context-based corrections. Then I'm going to be talking about the data set that I used and how I prepped it, and the alignment, which will make more sense once I get there. And that's actually just going to be a little piece of my presentation, because the big chunk is going to be machine learning. So I'll have another overview of that on its own. But first, let's talk about the OCR process and what OCR is. So OCR stands for Optical Character Recognition, and it's the idea of taking a picture of a text and scanning it, and then pre-processing that, which is converting the potentially black and white image of text into a map in a 2D coordinate of little pixels per se. And so when you're doing that map, for example, here we can see the number 8 is going to be represented like this in a little 2D array. And so we are trying to identify that those order of pixels represent an 8. And so this is a complicated process of its own, but once you actually go ahead and decide this is an 8, you go ahead and you create your OCR text. Now, there are going to be some OCR generated errors. For example, the sentence "the Federal Register Volume 1" may be misread as the Federal Register. So as you can see, the R gets replaced with an H. This is a typical error because from an OCR standpoint of view, the R and the H look very similar. They have a vertical line, and then they have a little arch coming out. Now the difference being that the H has the full arch that comes down versus the R, which kind of just stops halfway. Of course, font variations and things like that make this a little bit more, for some fonts, more related, and for other ones they look more different. And so the errors that you may get from OCR are going to be very different than the kind of errors that somebody would make typing. With typing, they miss the keys, and I'm looking at a keyboard here, instead of pressing A, they might press a W because it's very close in the keyboard. They're not going to press, for example, R and H. R and H are relatively close, but there's about 2 keys between them. And so it's more unlikely for that to be a spelling error somebody would make in a typing point of view. Handwriting point of view, it would be very, very weird that they just flat out misspelled register as register. It's more easy that they may have written it and it looks to somebody else like an H. So with that, I want to say that OCR errors are very different than spelling errors. And so essentially, that stage where we are fixing those errors is considered to be the post-processing stage, where we're trying to improve text that has already gone through the process of OCR, and we no longer have the original text. In a way, it's the equivalent of somebody proofreading a text to find more errors. And so what are some of the ways that we can correct those errors? Well, think about proofreading, as I was talking about. When you're proofreading somebody else's assignment or text or essay or something, and you find a word that you don't know what it means, or that you think it's wrong, you have an idea of the context of the surrounding words to see if those give you an indication of what the writer or author was trying to say. And so we call those context-based corrections, because we're looking at things around the word and seeing if they give us a hint. Other ways of fixing it is something like a confusion matrix, where you know what kind of errors you typically make. So like if this is a very popular error because the R and the H look very similar, well, if we see something that it has the word register, which is not a real word in the dictionary, but we know that R and H is a common type of error, then we're going to give that higher priority and say, okay, register is a potential candidate because the H to R error is a very popular error. And so, from there, here's an example of context-based corrections and what we can do, for example, with register. Like, just look at the word register there, and if later in the sentence we have the word registrar, we could use that context that we're talking about registers in a way to correct the word register from register and things like that. And so to be able to do it in a computer, though, it's not as easy as a human where we can read it and understand those kind of connections, right? For our computer, we need to train it to understand what context is. And for that, we can use different corpuses. We have, for example, Google Web 1T. Google Web 1T is a corpus that has up to 5 grams, where they took the entire internet, downloaded it per se, because it's Google, and they extracted 5 n-grams. So think of, they extract 5 words. The first 5 words are the first web page of the entire internet, and they generate a 5-word combination. And then they slide it to the next one, and they generate the next 5 words. So here we have an example here. If you can see at the bottom, I can use my mouse to point. Yeah, okay, perfect. So here we can see we have the brightly colored birds in Wiley, okay? So these are 5 words. And the original sentence is a tropical group of brightly colored birds in Wiley belong to the family something. And so we take those words and then we slide it and take the next 5 words, but just 1 word ahead. So instead of reading brightly, we're going to read belong. And so it keeps sliding forward. And so what we can do is, if the word birds is misspelled, and we historically see that the word colored comes very often before birds, we may see that that's a potential candidate to correct the word birds or the word colored. And so, for example, here you see we have supplement derived from, and that's a very popular 3-gram phrase. You can see it appears in the entire quote-unquote internet that Google used at the time, which was about 20 gigabytes of text files, 21 gigabytes. It appears very often. It appears 26,100 times. And so that's compared to something like supplement that depends entirely, which doesn't appear as often. So what does this tell us? Well, what it can tell us is, if we have the word supplement and we have the word from, and the word that's incorrect is the word derived, well, we know that the word supplement and from surround the word derived, so the word derived may be a candidate to correct those kinds of things. And so there's more than just Google to be able to generate these corpuses, because you can get it from anything. And in one of the papers that we were pending publication, we actually did it with Wikipedia. We use Wikipedia as a training corpus. You can just use the text itself. In this case, we are using TREC-5, which is an OCR data set, where it has the original data set and it has a 5% character degraded data set where they basically scanned a bunch of, I believe they're newspapers, and so federal newspapers of some sort. And so they have the source file, which is actually with markup language, and then they have the actual newspaper, which then they rescanned and then went ahead and threw it in there. And then they also have a 20% error, but that's, I think, artificially, or they rescanned it multiple times or something. We're not looking at that one. We're looking at the 5%, which is more of a normal kind of error rate for OCR text in general. Okay, so basically that's what context-based is. And our data set is a TREC-5. And so with context-based correction, I'm going to go really fast here because this is actually a different paper. What we do is, like I basically said, is we get those 3 grams for a word that we think is misspelled, or for the and to do that is, if we have, for example, the supplement depend on. Suppose that the word depend is misspelled, but the word supplement and the word on before and after is what we're going to use as context, and then we're going to look in our chart and see how many times or how many possible words appear that have a word 1 as supplement and the word 3 is on. And we have the word depend, we also have the word depending, we also have the word depends, and there's probably more. And so ultimately, those are what we're going to do to generate candidates, and then we refine and we verify. How do we verify? Well, here we have the original text and we have the degrade text, but those 2 texts are not actually side by side. You know, we have a file that's the correct text, and we have a file that's the incorrect text. And here I'm talking about the cleanup, but as you can see, there's some markup that is start a document and end. So we have doc. So like here we see doc, and then there's a doc ID all the way to the bottom where it says doc, you know, and we remove some of those flags, but some of that markup language. But before we do remove it, we keep track of each document, right? And so I'm going to fast forward to this. The trick here comes in as follows. So here you have 2 sentences. The register in T&E building is next to the registrar's office, okay? And then that's going to be the OCR text, which has an error. It has the T&E, which is wrong. On the bottom is the correct text, which is the register in the building is next to the registrar's office, right? And we know the correct text because we have basically the ground truth, which is the source file. The problem is, how, when you're doing whatever magic you're doing to correct a text, how do you check yourself? Of course, you can go look at the original text and see, did I make the right suggestion? Okay, now multiply this in thousands of corrections that you're trying to do. So you got to automate this process, right? So how can you line up both text? Well, it turns out that it's a pretty hard problem. It's actually NP complete. And so one of the papers that I did is an alignment algorithm that has a little bit of a heuristic in it because, of course, NP complete, you know, I'm not trying to say P is equal to NP here. I'm just trying to say that with a heuristic, we can do this much faster than something, you know, on the level of NP complete. And so basically, you know, if you want to see more about that, you can look at these two papers. At the bottom one talks about the alignment algorithm, which basically allows us to line up the text so that we can check ourselves to see if the suggestions we're making are correct. So anyways, that kind of concludes previous work that led into this. So we were able to generate all these candidates and things. And so now we're going to throw in machine learning to help us, improve what we're doing. And so what I'm going to do is I'm going to first talk to you about the features that I'm using. I'm going to talk to you about attempting regression, binary classification, logistic regression, how that didn't work out very well, probably because the data is not linearly separable. And then we threw SVMs, which is going to be the main focus. And then I'm going to briefly talk about things to improve the results from the SVM, which are, you know, normalizing your data sets and balancing classes, which are pretty standard things you can do to improve your output. And after that, I think we'll be pretty much out of time. If we have a little time, we can discuss some of the errors that I ran into. So as a refresher, there's two kind of machine learning. Big topics, you know, supervised and unsupervised. In this case, we are working in supervised machine learning. And so within supervised machine learning, we have two categories. You know, we have regression and classification, classification being accepting or rejecting. In this case, what we have is a list of candidate words that we've generated with the previous research that I showed. And now we're trying to decide, is the candidate a good one or not? Like, do we accept this candidate word as the correct word to correct? Or is it wrong? You know, we have a bunch of candidates. We want to say is which one's the best one by saying which one do we accept. And so, you know, I talk about logistic regression, which I think I can skip for now. More importantly, I want to talk about SVMs because that's really the focus of this. And so here's the really cool thing about SVMs versus something like log regression. You know, log regression, there's a lot of magic you can do with base function expansion and things like that for non-linearly separable data. But in the most basic sense, you usually with something, if you're going the most easy way, you have to have linearly separable data with logistic regression, right? Support vector machines, on the other hand, you cannot have data that is not linearly separable, at least in the basic sense, because otherwise they don't work. However, we all know we can apply the Kernel Trick to lift the feature space into a higher dimension, where we can actually achieve non-linear classification, because in the higher dimension we have the ability to linearly separate the data with a hyperplane. Here's an example of that. You know, we have data on the left here that is not linearly separable because it's a circle, and even though we could draw a circle there and separate the data with 100% accuracy, you know, the SVM cannot do that. What does it do? You throw in a kernel and it increases the dimensionality into the picture on the right, where now you can put a hyperplane right in the middle of those two data sets and do it. In this case, what could that sort of kernel be? Well, very easy. In this case, there are, if you see the X and Y label, it might be a little misleading, but coordinate 0 is actually right in the center, although that's irrelevant, it could be anywhere. And so using that, what we're saying is the Z dimension is going to be the distance from that 0 point. And of course, all the ones that are closer because they have a smaller radius are going to be lower, and the ones further are going to be higher, which is why in the third dimension things are separable. So of course you have to know your data to get to do things. But the beauty about the kernel trick is that you have all these different kernel functions, and polynomial, which I believe is the one that we mostly focus on, but we want to try RBF later on, get to do this for you, and you don't have to worry too much about the magic that's happening behind, right? Very briefly to refresh your mind on SVMs, I have a video on SVMs on my YouTube channel, so you can check it out, where I talk about SVMs for like 2 hours or more. So I'm going very fast on this, but with SVMs, you know, you have your support vectors, and which is why it's called support vector machine. And so they're trying to find the separation between the two linearly separable data, you know, types, points, whatever you call them. Whereas linear regression, as you can see, any of those lines could work. But with SBMs, we want that, the third one, so the one right here, because it separates it at best, which in a way decreases the chances that our model doesn't generalize well, or it's overfitting or things like that, right? Okay, so now that I refreshed your mind on SBM, let's go ahead and jump right into what our features are that we're going to throw into the SBM. So we're trying to correct misspellings, right? OCR generated errors in a way. And so one of the important things that we want to do is how close is the word that is wrong with the correct wording going to be? And that's our Levenshtein edit distance, right? There's how do we convert one word into the other one? So the wrong word into the potential candidate. What do we have to change, substitute? What do we have to insert, or what do we have to delete? And so that's a very, very useful value for us, because the higher the edit distance, or the Levenshtein edit distance, the less similar a word is. The smaller the number, the more similar. Of course, two words that are identical have an edit distance of 0. So that's going to be the first feature that we're going to keep track of. Next, we're going to keep track of the confusion matrix. So the confusion matrix is going to maintain that record of what is a popular error that you make with OCR. So for example, here I went ahead and show you the most popular ones that we saw. I guess the one that makes most sense here is the L to I. You can see how it's very easy for a scanner to misrepresent an L into an I, because maybe it sees a little dirt, or it doesn't read the straight line, or vice versa too, actually, you know. The dot from the I might be so close to the stick of the I that it just combines them and things like that. There you see H and R. As you can see, it's a very popular mistake. I think the Y and K also look similar because of the diagonal lines, or the Z and the K. The one that I found interesting is S to blank. So this is actually an insertion or a deletion of an S, because it just doesn't detect it. Maybe because the S is so thin in some fonts that it disappears. So anyways, that's going to be the confusion matrix, which is basically how popular is a incorrect substitution, insertion, or deletion. So as you can see, substitutions are going to be the first set here that you can see here. Here we can have, for example, an insertion and a deletion, right? So that's going to be the second one. The third one, the unigram frequency, I believe I have, here's a full list, which I have as part of it in the paper in our case. And I guess I'll have an example for the other one. But let me talk to you about what unigram backwards and forwards are. Unigram frequency is how popular is our word. And by that I'm saying how popular is the candidate. Is our candidate word supercalifragilisticexpialidocious, that is a very, very rare word to see? Or is it something like da, where it's super, super popular, right? Because in that case, we're going to play a little game of statistics and say that if given the choice between like 10 words and one of them is a super popular word, the odds are that most of the time it's going to be the super popular word, the correct candidate, right? However, you know, we're not just using that as a decision maker. Otherwise, we would just have one feature. We're just saying that's going to be one of our potential features, is how popular a word is. And then backwards and forwards bigram frequency is going to come back to the idea I was talking in the beginning with context space. We have word 1, word 2, and word 3, right? Word 2 is the one with the error. So what we do is we look at word 1 and word 3, and we're hoping that the first and third word, you know, that we're hoping that an error is existing only in the second word and not in the first and the third, which is not always the case. And, you know, this is something that we have to deal with. But, you know, ideally, the word before and the word after are spelled correctly. And if not, then we have to deal with that in other ways, which I do. You can read other papers and so on. But ultimately, we can see how popular word 1 is and word 2 as a pair of words. You know, like, for example, eating food. Eating food is probably a very common two-phrase word, right? If you see the word eating, it's probably followed by food. Now, is it the only one? Of course not. You could say eating cookies, eating chicken, you know. But I'm saying eating food is probably very, very popular if we were to, again, do something, Google or go on Wikipedia and see how often that phrase is. And so we're going to, again, play statistics and say whatever has more frequency of that pair is a higher chance of being the right candidate. And so we do that with the word before and the word after. Okay? So, you know, again, we're using our data set, and here's some statistics about the data set. The only thing that I want to point out is that when we generate the data set from the candidates, so as you can see, let me walk you to the first line, or actually for that, let me look at this slide. So we got 337. Here, let's look at the second line: 1, 918, 82, 82, 0, and 1. Right. That means that the word register to register, which is our candidate that we're suggesting, the edit distance is of 1 because all we replace is H to R. The frequency of that H to R replacement is 918. The unigram frequency of how often register appears in a corpus is going to be 83. The backwards bigram, so how often does dot appear, is 83. What does that mean, by the way? That means that all the cases that we have seen in the training set basically have the phrase dot register. We don't have any case where register is followed with another word, where it would be something like federal register. That's just what we're saying. Forward bigram frequency is saying that we have no examples where the word after is followed by something else. Now, I don't know what the next word is. I have it back in the beginning, but it's just saying it doesn't appear in our training. And what is our corpus? In this case, we're using Google 1T, but we could be using other things as well. We did try other things. In fact, I'm not 100% sure that Google 1T was in this case. We also have the Wikipedia data set. We can also use its own data set. So we can also use the TREC data. And we're hoping, again, this is playing game of statistics, but we're hoping, and this is kind of losing that game, because we're hoping that other cases where the phrase happens, the OCR error is not present. That's not always the case, because usually if a OCR scanner misrecognizes a T for an H or an R for an H or something, more than likely it's going to recognize that same letter multiple times. How do we fix that? We can always train by hand a percentage of the text and then use that to train the model so that it can fix other cases of that. So anyways, the idea is you generate the data set like this. And so now it's just a list of numbers, ultimately, which, machine learning. Numbers are much easier to plug in than words and other fancy things. So we generated candidates in the previous project. And so what you can see here is that there's an imbalance that we're going to talk about later. We have a lot of incorrect candidates that can be generated by the previous work. And we also have a lot of correct candidates, but a much smaller ratio. We have 14,000 correct candidates and 310,000 incorrect candidates, okay? That's saying, and you can see it here in this example, look at all those. Only one of those is, which is the second one, a correct suggestion. The rest are bad. And in this case, you can see that the machine learning algorithm should have no problem doing this because all those numbers are higher for that specific case. So that's an easy one, But that's the problem that we're going to have to deal with, okay? So we threw in logistic regression just to test it out. We just achieved 92% accuracy, but this was just on the training set itself, right? That's, of course, useless. If we go ahead and try training and test set, as you properly should do things, we're going to do train, test, and validation, but in this case, we're just experimenting, so we did train and test. Accuracy drops down to a 4%. What does that mean? It was trying to overfit with the first case, but it was practically useless. That's why we go into LibSPM, which is an implementation of support vector machines, which is also actually what Scikit-learn uses. But we decided to go with the source, which is LibSPM. Here's an example on the website that you can do, and you can see how cool it separates colors and things like that. And so, again, you can watch the other video that I have if you want to talk about LibSPM. But in this case, we did Polynomial Kernel, and we just did it all on the training data set first. And again, that doesn't really do anything. I mean, yeah, sure, it's a little bit better than before, 92, but again, we're just doing it on a training set. There could be overfitting. The real test is going to be, of course, when we do 80-20 distribution, train and test. In this case, we still kept a 93% accuracy. That's much better than 4%. Our precision is 85, which is pretty good, but our recall is 10%, which is pretty bad. What is precision and recall? Just as a refresher, we have a confusion matrix, but in this case, it's not the confusion matrix I was talking about before. It's the true positives and false positives, false negative, and true negative confusion matrix. Okay, so from that, you can see there your formulas for precision and recall. The best way to think about it is when you have high precision, it means that there's very few false positives, but that doesn't tell you anything about the false negatives. When you have high recall, it means that there's very, very few false negatives. Now, what's a false positive? In our case, a false positive is accepting a wrong word. A false negative is not accepting a correct word. So both of those are, of course, bad. So I want to have a little discussion about this and talk about the recall and basically what I said. So, okay, so, those are not bad values, accuracy is pretty good, but the recall is pretty bad. So what the recall is really telling us that it's low is that we're not accepting words that we should, which, it's kind of bad, right? So, okay, what do? Well, the two most basic things, 101 machine learning that you can do is you can try normalizing your data set and balancing your class distribution. So why do we want to normalize our data set? Well, as you can see, our values vary very greatly. The confusion weight especially is very high, like can go very, very high. Those are big numbers. And the other ones like frequency of unigram and bigram are not as high. And edit distance is super small. Typically, over 4 is too much. So, what can we do? Well, we can rescale the data using min-max or other things like z-score standardization. And so, standard deviation is one option, but it's not going to be the best, as you can see. And then the other one, I found this really cool picture on the internet. Min-max is actually going to be the best thing. What is min-max? It's making your data from a range of 0 and 1. So you take the biggest value of the data, you take the smallest value of the data, and those are going to be your min and max per se, your 0 and 1. And you fit the data, everything in between, right? And so here's an example of what the data looked like before and what it looks like now after it's been normalized. And so we went ahead and tested that with the normalized data set. And so actually, first we tested it with the standardized data set, which is the standard deviation, and it just failed epically. 5% precision. Recall was high, but I mean, that's useless when you think talking about precision being super bad and 6% accuracy. What it really means is that there were false less negatives, but that's because the model was basically just accepting everything it took, which is how it got that, basically. Of course, when we try normalization, we achieve much better results. We can see that the accuracy is 96%, and precision and recall especially is a lot higher. So this is actually going to be one of the best things as well. But this is just training. So let's go ahead and do with training and test. With training and test, it actually performed relatively better, which is interesting. We have precision 91% and recall 58%. And it actually also speds us up a lot. This took 6 minutes and a half to run versus hours with the normal data set without normalizing it. And it took 130,000 iterations. And it generalized well with that accuracy, 96%, slightly higher than the training one, actually. And there's a little bit of more false positives. However, and then the original data set that was not normalized. However, the precision went up because we had more true positives. Which means more successful corrections. In this case, we actually had before 494 corrections, and now we had almost 3,000 corrections, 2,600. So that's pretty good. And the increase in recall from that increased to 58% from 10% means that false negatives decrease from about 4,000 to under 2,000, which means that less incorrect words are accepted. So overall, normalization was a huge success, and that can be seen in our F-score that went up dramatically from 0.19 to 0.71. That's very, very good. We now have successfully corrected 58% of the errors. I went ahead and also tried out in Scikit-learn. Should give me the same thing. It relatively did, so I just threw it in there. You can find out more information on later on. You can download the data set yourself. Finally, let's talk about over and undersampling. So again, we have that big and balanced data set. It's actually 4.5% is only belonging to class 1. So what is oversampling and undersampling? That's when you artificially increase one class of the data set so that you can have it balanced. So instead of having 13,000 of one data set and 400,000 of another data set, you extrapolate your data or do other things to it, to interpolate or whatever, to create more points out of nowhere, really, which can cause other problems, but ultimately to try to balance it, right? And so you can see here that kind of happening as you can see from the top, which is the original data, and then the different oversamplings using assign, smooth, or random. As you can see, it sort of increases the concentration of points. Like the purple points grow a lot more than the original data set, which helps the data set to balance itself. And so we use SMODE in our case. And so let's just skip to the training test. We lowered our accuracy a little bit to 91%, but our recall went up very dramatically to 91%. And that's the highest that we've had so far. Before it was 58%, so as a comparison. And the accuracy went down from 96 to 91%. And overall, because of that, the F score went down from 71 to 59. But so I would say that the imbalance model is the clear winner. However, you can apply ensemble learning to learn from both types. You know, the balanced version of the data set and then the imbalanced version, and you can use both to help you because the recall is, I believe, the highest that we've seen, and so that's a good thing. As you can see here, our false negatives are pretty low, and so that pretty much draws it to an end. As I was saying, I wanted to talk about what kind of errors we had, and so ultimately, the two kind of errors that we have are false positives and false negatives, and so what can we do? Well, you know, in this case, one of the issues that we're having is we need to do a little bit more cleaning of our data set to avoid this kind of errors and to use some stemming potentially or things like that, because it can miss words because they're very similar in the heart of the word, but maybe they have a punctuation or capitalization or other things. So, you know, ideally, there's a lot of things that we can do. And so to summarize, you know, we created our candidates and we normalized the data set. I showed you how to normalize, balance it. And in the future, we want to create more features. Like I said, do some stemming and things like that, do some ensemble learning. Overall, I would say that our precision and recall are acceptable. And again, think about the positive here that we're correcting words without creating more problems than we're solving. And yet again, we don't, I mean, even though we say we accept or reject a candidate, we can still, you know, if we can still feed this as a suggestion to a final end user, you know, and then have him make the final choice. So ultimately, this doesn't have to be a perfect score. A perfect score is practically impossible. And most people that say they have such a high F score or precision recall are making it up and they don't have the data to prove it. Ultimately, we want to do the best we can while not having it just work for our very specific data set. And so that's going to conclude our presentation. I hope that you learn a little bit about SVMs and about our paper. If you would like to find out more, you can always come check out UNLV on the website, and you can contact me and I can give you some information, check out the source code and things like that. And I thank you for your time. I hope that you have a wonderful day, and thanks again.